Welcome back for another deep dive from Peaceful Rooster Experience. Today, we're taking a look at the evolution of optimizers in Apache Spark.
It's quite a story.
It is. Our listeners are going to learn just how Spark went from, well, requiring expert-level tuning
Oh, yeah.
to becoming this data processing powerhouse it is today.
It really is a reflection of just broader trends in data processing, this constant push towards making things faster, easier.
And more scalable. And to do that, we've got a whole stack of articles,
Yeah.
research to guide us. We'll cover the early days of manual RDD optimization to some really cutting-edge techniques like...
Oh, like adaptive query execution.
Exact.
Vectorized processing.
Let's kick things off by rewinding back to Spark's early days.
Okay.
When distributed data processing was, well, a bit of a Wild West,
Yeah, Spark was all about those resilient distributed data sets.
RDDs.
And they were revolutionary, really, for their time because they provided this way to process data in parallel.
Across a cluster of machines.
Right, and this concept of lineage, so tracking how data is transformed, was groundbreaking for fault tolerance.
So that means that even if a node in your cluster crashed,
Yeah.
Spark could actually reconstruct the lost data.
You got it. Without missing a beat.
That must have been such a relief for developers back then.
Oh, absolutely. But there was a catch.
Oh.
To get that performance out of RDD's users really had to have a deep understanding of how Spark worked.
Internally.
Yeah, they had to manually optimize things like the data partitioning, caching, even task scheduling.
It sounds like a steep learning curve.
It was a steep learning curve.
And I bet that limited Spark's adoption, especially for folks who weren't, well...
The hardcore Spark gurus.
Yeah. You're right. So, for example, if you wanted to do something simple like calculate an average with RDDs, you'd have to write code to manually load the data.
Map it to extract values.
Use those values to get the sum and count.
Yep.
And then finally compute the average.
And each step you have to think about, how is the data distributed across the cluster?
That's a lot of manual effort for a seemingly straightforward calculation.
It is.
So how did Spark evolve to handle all this complexity?
Well, the turning point came with the introduction of Catalyst in Spark 1.0. Catalyst. And this was a game changer because it brought automated optimization to Spark SQL and data frames.
So Spark started doing some of that heavy lifting itself.
Yeah, taking some of that burden off of the developers.
I like that.
So Catalyst works by creating both a logical and a physical plan for each query.
Okay.
The logical plan represents what the query intends to do,
All right.
and the physical plan determines how it will be executed.
So it's like having an architect draw up a blueprint for a building, and then having the construction crew figure out the most efficient way to build it.
I like that analogy. That's a great analogy.
So Catalyst uses all these optimization techniques like predicate pushdown.
Right, so moving the filters closer to the data source, which reduces the amount of data that needs to be processed.
Which makes sense. Filter the data early on and avoid unnecessary processing later.
Exactly.
What else?
Another key optimization is join reordering.
Okay.
So Catalyst analyzes the size of tables involved in a join, chooses the most efficient join strategy. This can significantly reduce the amount of data shuffling.
Oh, across the network.
Across the network, exactly.
The Catalyst, like a traffic cop,
Yeah.
optimizing the flow of data within the Spark cluster.
I like that.
So what kind of performance impact did all these optimizations have?
The impact was substantial. So Catalyst made Spark SQL and data frames much easier to use, and they were significantly faster.
Really?
Yeah. Queries that used to take hours
Wow.
could now be completed in minutes.
That's impressive. But I have a feeling Spark didn't stop there, did it?
You were right. There were more optimizations on the horizon.
More.
Spark 1.5 saw the arrival of Tungsten.
Tungsten.
Yeah, a project focused on optimizing the physical execution of Spark queries.
So if Catalyst was about optimizing the query plan,
Yeah.
Tungsten was about optimizing how that plan is actually executed.
Exactly, you got it.
That's it.
Think of it as fine-tuning the engine of a race car to squeeze out every last bit of performance.
I like that.
So one of the key innovations in Tungsten was whole stage code generation.
Okay.
This technique compiles entire stages of a query into native machine code, eliminating the overhead of interpreting individual operations.
It's kind of like taking a multi-step recipe and turning it into a one-pot meal.
Yeah.
Streamlining that entire process.
Exactly, you got it. And the results were remarkable.
What happened?
So tungsten, combined with improvements to memory management and data structures, led to significant reductions in query execution time.
Oh, wow.
And memory consumption.
So Spark was becoming a lean, mean data processing machine.
It was.
But I have a feeling there are even more chapters to this optimization saga, right?
Absolutely. And we will delve into those advancements in the next part of our deep dive. As Spark's capabilities grew, developers realized that even those sophisticated optimizations of Catalyst weren't quite enough to handle the dynamic nature of real-world data.
So it's like having a perfectly tuned race car, right?
Yeah.
But then you face these unexpected road conditions mid-race.
Exactly. That's a great analogy. And that's what led to the introduction of adaptive query execution, AQE.
AQE.
It's a 3.0. Yep.
Okay.
And this brought a whole new level of dynamism to Spark.
Really?
Yeah, it allowed it to adapt to those changing data characteristics during query execution.
So Spark could think on its feet.
Yeah.
And make adjustments in real time.
Exactly.
Tell me more. How does it work?
So AQE continuously monitors the progress of a query and collects statistics about the data being processed.
Okay.
And then if it detects that the initial plan is no longer optimal, it can dynamically adjust that query plan.
Based on runtime information.
On runtime information, exactly.
So it's like having a self-driving car that can reroute itself based on traffic conditions. Road closures, unexpected detours, all of that.
Yeah, a great analogy.
What kind of adjustments can AQE make on the fly?
So one example is handling changes in data size.
Okay.
So imagine you're joining two tables, and one table turns out to be much larger than expected.
Right.
Without AQE, Spark might just stick to that initial plan.
Which could lead to performance bottlenecks.
Yeah, or even memory errors.
Yikes, that sounds like a disaster.
It does.
How does AQE save the day?
So it can dynamically switch to a more suitable join strategy based on the actual data size.
Okay.
It can also repartition the data to ensure optimal parallelism.
Yeah.
And it can handle cases of data skew where certain keys have disproportionately large amounts of data.
Gotcha. So AQE helps Spark avoid those nasty surprises that can completely derail a query's performance.
It does, yeah.
Like a safety net built into the execution engine.
Yeah.
What impact did AQE have on the Spark ecosystem?
So it was a major step forward in making Spark more robust and easier to use.
Okay.
And it reduced that need for manual tuning and allowed developers to handle these unpredictable workloads more gracefully.
This brings us to another really exciting development in the Spark world.
Yeah.
The emergence of Delta Lake.
Yes.
And its impact on data lakehouse architectures.
Yeah.
Can you tell us more about that?
Absolutely. So Delta Lake is this open source storage layer that sits on top of existing data lakes.
Okay.
Think of it as bringing order and structure to, well, the sometimes chaotic world of data lakes.
Transforming a data swamp into a well-organized library.
Yeah.
Complete with shelves, catalogs,
Yes.
easy to find information.
That's a great way to put it. And Delta Lake offers ACD transactions.
Oh, wow.
Schema enforcement and data versioning, so it's making those data lakes more reliable.
And suitable for those demanding analytical workloads.
Exactly. Yep.
So those features sound like they're real game changers for data lakes.
They are.
But how does Delta Lake actually optimize Spark performance?
So Delta Lake introduces several key optimizations that work really well with Spark.
Right.
And one of the most significant is file pruning.
File pruning, okay.
So Delta Lake maintains metadata about the data stored in each file, allowing Spark to selectively read only the files that are relevant to a query.
So it's like having a detailed index.
Yeah.
For your data lake, you can pinpoint the exact information you need.
Exactly. And Delta Lake also supports data skipping.
It is skipping.
Yeah, which goes even a step further than file pruning.
Okay.
So by collecting statistics about the data within each file, Delta Lake enables Spark to skip entire files.
If they don't match the query's filter criteria.
You got it. So Spark doesn't even have to bother reading those files.
That must save so much time.
It does. A ton of time and processing power.
And there's more.
There's more, yeah.
What else?
Delta Lake also employs a technique called Z-ordering, which arranges the data on disk to optimize data locality for these multidimensional queries.
Like arranging books in a library based on multiple criteria. You got the author, the genre, the publication date.
Exactly. And Z-ordering ensures that data relevant to specific filter conditions is all clustered together.
Gotcha.
Which minimizes the amount of data Spark has to read.
So these optimizations sound incredibly powerful.
They are.
What kind of performance gains can we actually expect from Delta Lake and Spark working together?
Well, the impact is significant. Queries that used to take hours on traditional data lakes can now be completed in minutes or even seconds with Delta Lake.
Really?
Yeah, it's made data lakehouses a viable alternative to traditional data warehouses.
So it's amazing to see how Spark has evolved from this manual RDD tuning
It is.
to this sophisticated self-optimizing system
Yeah.
integrated with these powerful data lakehouse technologies.
It's a testament to the constant innovation happening in the Spark community.
But the optimization journey doesn't end here.
No, it doesn't.
We're going to dive into some cutting-edge advancements
Yeah.
in our next segment. So we've seen how Spark has evolved from manual optimization to these self-tuning systems and integration with data lakehouses.
Yeah.
But where do we go from here? What's next?
Well, the future of Spark optimization is pretty exciting. One area that's got huge potential is AI-driven optimization.
AI-driven optimization.
Yeah. Imagine Spark using machine learning models to predict the best query plans.
Wow.
And automatically tune configurations based on historical data, real-time conditions.
It's like Spark making decisions based on its own experience.
Exactly.
That sounds like something straight out of a sci-fi novel.
It does.
How would that work in practice?
Well, these AI models could be trained on huge data sets of past query executions, learning patterns and relationships between those query characteristics, data properties, performance metrics.
Okay.
So, it could allow Spark to make much more intelligent decisions.
About query planning, resource allocation.
Yep, and even data partitioning.
So instead of relying just on predefined rules, heuristics, Spark could actually use AI to get better over time.
Exactly, yeah.
That's a game changer for developers and data scientists.
Oh, absolutely.
It would significantly reduce the need for manual tuning.
Yeah.
People could focus on actually getting insights from their data.
Yeah, rather than messing with Spark configurations.
So it's like having this expert Spark tuner built right into the engine.
Exactly.
What other advancements are on the horizon?
Well, another exciting area is hardware acceleration.
Okay.
We're seeing a growing trend of integrating Spark with GPUs and TPUs,
Right.
which are specialized hardware designed for that parallel processing.
So GPUs, those are already used in machine learning, deep learning.
Yeah.
How would they benefit Spark workloads?
So GPUs, they excel at tasks like matrix multiplication,
Right.
linear algebra operations, and other computationally intensive tasks.
Which are pretty common in data processing.
Very common, yeah.
So by offloading these operations to GPUs, Spark can really see significant performance gains.
Exactly.
So we could see Spark using GPUs to accelerate everything.
Yeah, from data transformations to those machine learning algorithms.
That's powerful.
It is.
And it sounds like Spark is becoming even more intertwined with this world of high-performance computing.
It is.
We also talked about data lakehouses.
Uh-huh.
We mentioned Delta Lake.
Right.
But there are other storage formats like Iceberg and Hootie emerging in that space.
Yeah.
What's going on there?
So deeper integration with those lakehouse storage formats is a key trend.
Okay.
We can expect to see more sophisticated data skipping techniques,
Okay.
optimized data layouts, better support for data governance, metadata management.
So making data lakehouses even more performant and easier to use.
Exactly. Yeah.
We've also touched on this idea of vectorized querying in open source Spark,
Yeah.
inspired by Databricks' Photon engine.
Right.
What are the challenges and possibilities there?
So adapting full vectorized execution in open source Spark is complex,
Right.
but it has huge potential.
Okay.
And the key is leveraging technologies like Apache Arrow, which provides that columnar data format, efficient data serialization, really well suited for vectorized processing.
So Arrow could be the bridge that brings those performance benefits
It could be.
of vectorized execution to everyone
Yeah, and the Spark community is actively exploring ways to integrate Arrow more deeply.
and to Spark's execution engine.
Exactly, which could lead to really significant performance gains.
That's great.
It is.
Well, as we wrap up our deep dive into the world of Spark optimizations,
Yeah.
it's clear that Spark's journey is far from over.
It really isn't now.
From AI-driven optimization, hardware acceleration, deeper lakehouse integration, the future holds a lot of promise for faster, more efficient, and intelligent data processing.
The continuous innovation in the Spark ecosystem is really inspiring.
It is.
And it's a testament to the power of open source.
Right.
Collaboration, this relentless pursuit of performance and efficiency.
Well, to our listener, we hope this deep dive has given you a good understanding of how Spark has evolved into this data processing powerhouse it is today.
Yeah.
And given you a glimpse into what's next.
Hopefully.
Remember, understanding these optimizations, it not only helps you write better Spark code,
It does.
but it also gives you the knowledge to navigate this always evolving landscape of data processing.
It does, yeah.
So from all of us at Peaceful Rooster Experience, thank you for joining us on this journey
Yes. Thank
through
you.
the world of Spark optimizations.
Yeah.